you gonna do for your Friday, Jeff?
You know, the same exact thing I do all Friday. Have my panic attack in the morning, and then come to schoolwork, put another panic attack before lunch, you know, maybe head home, sleep away, get fresh again.
Well, how the other
Now
people
they can lie,
you have 2 whole hours to yourself.
I know, well, I wish I could go collect data, but. We could go collect data, we could turn it on.
I'm still
She's sensitive.
thinking that I'm gonna see at the
She's
time.
doing
I'm hoping I can get my.
no, so she's looking at.
Yeah.
hourly rates.
But like,
So we're using a drive.
well, I'm down on it. No, it's 12 minutes. I'm like, we're usually talking about when I'm actually presenting.
You ain't got a stomach now?
I just don't know.
I need to stress for them, because it's like how,
Yeah, no.
Right?
That's, gotta help her, so.
I've been stressed and I
yeah, tomorrow, that's all.
Right. Kind of sucks though.
Yeah, this job's, in the job, monitor the water.
Monitor the water, I need to create water.
Identify sea turtles from their tracks.
I can do that.
This is like Jeff's ideal job. Survey for nesting shorebird.
Yeah, I keep trying to do shorebird work. No one lets me do it. I don't know why.
Identify false nests.
I think that's my good point.
False nests? Are birds really trick nests out there to use for researchers?
Are they?
I mean, you think that makes sense?
I make them all the time when I go to the beach.
Just throw out the researchers. It's like, I know that.
When I see them, when I see them, you can tell that they typically have badges.
Yeah.
Typically in the van that says, you know, university name. It's like, hey kids, hurry up, let's start making false nests. Then we just hide behind the bushes and laugh at them.
There's something a good time.
All right. That's where we left off. Had a question about the exam. They're gonna get graded. They're gonna be done on Monday. So, we'll get those done. The end is in sight in terms of remaking all these lectures. So we'll be able to get those done. If you're curious.
Are we having another exam before
We're
five?
probably only gonna do one more
Okay.
because we lost out on that.
Because I think
that
last
whole
week or the
2-week
week
block.
before was supposed to be our second exam. So
Yeah.
I wasn't sure.
Yeah, no, we lost out. What we'll probably do is this, when we finish out like the multi-way with like violating assumptions, then we'll probably do one more test. And then what we'll probably do is rush through like a correlation just so we can introduce like continuous variables and like these multivariate models. Yeah, because right now everything is factors. So kind of show you what we do. In terms of model simplification, it's the same. With the interpretation, you don't do 2Ps on a continuous variable. So it's pretty easy at that point. Anytime we have a continuous variable, doesn't really change anything. No, we can't have 3 weeks. Again, we lost those 2 weeks that really hurt. But oh well, it happens. All right, so jalapenos. How was it? Long? You're gonna see me back and forth. I'm gonna make a markdown document of this one so I have it. All right, so we're gonna need some packages. CAR, GBLMA, I'm gonna use those. I read in my jalapeno data, right? When we looked at it, we had low, medium, high. So watering frequency wasn't in the correct order. So I refactored it to make sure it goes from low, medium to high. All right. And then once we start checking out our actual data, we could do it any number of ways. All right. So when we look at our data, and this will kind of be a work through example. So if you get some stuff where it's like, well, I didn't get that, or why did you do that? Please stop. This isn't just like a complete review. There is something new in here that I didn't introduce necessarily. We covered it, right, in terms of including it in our analysis. We didn't talk about it. So if we look at the data, we can just go through and look at weight as a function of each of our variables. All right, and look at these plots just to kind of get an idea of what we might expect. Water, light, water, light, brand, variety. So what I'm going to do is just kind of look at all of these first. Oops. Why did I do that? Hold on, I know what it is. It's our new change. We'll have to do, let's just import the data set again. Because the stupid way that these things work, at least on mine. Take off S. Trains factors. Import. Imported it, refactored it. There we go. All right, so just one by one, water. All right, I'm not going to be surprised to find a difference between the high and at least the low and the medium. There could be a question of whether or not low and medium are different. Shade looks like there's an effect. Variety doesn't seem like there's any effect whatsoever. Early and mild seems like there might be an effect. All right. So just generally speaking, that's what I'm looking at. Since we have multiple variables, I can go ahead and do an interaction plot. Let's see this. With jalapeno, interaction plot, the one that we are plotting is weight. That's at the end, and if we do water and light, mess that up. Interaction plot. Wait. There it is. All right, so I look at that. Maybe this water-light interaction might not be significant. The brand probably isn't going to be significant. Maybe the variety, probably isn't significant, and that's just with one of the variables. So we would probably need to look at all of them. So light and variety, nah, that's looking pretty good. What about light and brand? Nah, probably not an interaction. What about brand and variety? Parallel. Kind of question. I'm questioning whether or not I'll see any sort of interaction effect. I think it covered all of the combinations. But it's not to say that we don't detect. We don't detect an interaction, because the way that analysis goes is we're going to remove terms that have an effect, account for that variation, and look to see, does any of these other terms account for additional variation. So we have our data, we've got 4 independent variables, we've got 1 dependent variable. That dependent variable is a measurement variable. We want to use an ANOVA an ANOVA to determine if weight differs. So I'm going to create my full model right off the bat because I'm going to check my assumptions. And what I'll do is do GVLMA on our full model. There it is. And take a look at it. And right now the global stat looks good. All right. So p-value is 0.33. Doesn't appear to violate any sort of assumptions. I can look at the plot, the residual plots, and you're going to see the same thing. This looks random. Random. That looks random. That looks normal. That doesn't look like it has any increasing or decreasing trend. And our outliers, again, it all looks pretty good. GVLMA and residual plots give us the same thing. So it looks like we're good. So now we're on to model simplification. And this is the long part, right? All right, so we made full model already. All right, so I'm going to look at mod.full. And we start at our highest interaction level. That's not significant. So now what we need to do is remove them, right? Copy and paste. Type all. There we go. All right, so I'm going to use update. And first up is I'm going to remove that 4-way interaction term. Update it, and then look at my ANOVA table. And I get this. So again, we look at the highest order interactions. These are the 3-way interactions. And what we're going to target is remove the highest p-value first. So we're going to remove these, all right, and then keep removing them. So we've done the 3-way. Now what we're doing is removing the water light variety, checking out the ANOVA table. Well, we still have a non-significant interaction. So I'm going to update it. Look at the ANOVA. Still 2 of them, non-significant. So again, look at this. Look at the ANOVA table. We're going to remove that 3-way interaction again. And that gives us, when we update it, a model with only 2-way interaction. So you can see just the pattern is we've gone from 3-way down to mod.2-way. So now these are the only 2-way interactions are in the model. And we're looking at these. Now there's 6 of them. And I can already see 1 is significant. So we're not going to remove that right now. Right? Maybe it changes. But right off the bat, what we have to do is start at the highest p-value on water brand and work backwards. So the first model, we remove water brand. Take a look at our ANOVA table. Next up is water and variety. That has our highest p-value here. Water variety. Take a look at our ANOVA table. Now brand variety, that's our highest p-value. So we're going to remove that. Look at the ANOVA table. Light and variety. That one. Look at our ANOVA table. And we have light and brand to remove. So remove that. Take a look at the ANOVA table. And now we have our significant 2-way interaction. Right, so the next step then is to look at the main effects. All right. But we're not really going to look at this table. right, we have a two-way interaction. All right, we have a significant two-way interaction. How do we proceed? Can we just go through and remove brain? That's it. Again. What is this? What's the meaning of the p-value for brain?
This is my p-value.
By brain.
What you're looking for?
Okay. Continue with that. What's the other specific with that? Well, we've already eliminated it, so yeah, we can remove it. So it's not part of our interaction term, so that's good. All right. That is the p-value. Brain is not a significant predictor of weight. Under what conditions?
Under all conditions for other variables, right? Under any light level or water level. Or so and so.
Almost. So this is a type 2 ANOVA table. Right? This is what we did. What does that mean? Oh. What is a type 2 ANOVA table? Go back and look in your notes. There's type 2 ANOVA table. What does that mean? What'd you find?
So the type 2 p-value takes the effect of the variable after it comes for all the other variables at the same or lower level.
All right, so it's a p-value of that variable after accounting for all other variables at the same or lower level. So the water-light interaction, that p-value is the probability that water and light is a significant explanation of variation after we account for water, light, brand, and variety main effects. All right? This p-value of brand is the amount of variation that's explained by brand versus lack of a significant amount of variation explained by brand after we account for water, light, and variety. What about the interaction? That's significant, right? Shouldn't we account for it if we're going to continue simplifying our model?
Yep.
So what type of ANOVA table should we now start using?
Type 1.
Oh, we got it. Dueling types. Type 1 or type 3?
Do not use type 3. So I'm going to assume type 1. And it also says, yeah, but up there it says the proper type of ANOVA table is type 3.
So
Oh.
we introduced type 1, type 2, type 3 in terms of looking at it as your total ANOVA, total simplification. All right. So if you just stop there, you're right. You really shouldn't, because it can lead you down the wrong path. But here we need to account for this interaction term. We need to account for that amount of variation if we're going to continue looking at the rest of these variables. Because what sense? We know there's an interaction. Why should we ignore that just to see if brand has a significant effect? All right, so we have a significant two-way interaction. The table above is a type 2 ANOVA table, which means that P equals 0.4136 for brand is after we account, God, that's horrible grammar. after we account for water, light, and variety. It does not emphasize that. All right. So when we use a type 3 table in this aspect, it's going to allow us to account for that interaction. All right, so type 3 is going to allow us to assess the main effects when we have significant interaction terms. And that's basically going to apply. Once you get your significant interaction terms and you start looking at the main effects, at that point we should now switch to a type 3 table just to continue using that interaction term in our model. All right? So I'm going to take this ANOVA make it type 3 table. And what you'll see, there's basically no effect. Minimal if any effect. Generally, that's what you're going to see. That interaction switching, at this point in our simplification, it's going to have very, very minor effect whatsoever. All right, so what we're going to do is, this is not significant, brand is not significant, so let's go ahead and remove it. So did you guys get to that? Get to that point. These. So remove brand, and just for comparison, you can see that that brand, the p-values didn't change because we're so small, but what changed is the change in the f values, the sum of squares, basically, right? Sum of squares. Now, with the sum of squares, we count the type 3 tables accounts for the intercept, but you can see 3353 versus 30. Let's see here, versus 4414 or 4114 and so forth. That's kind of what we're doing. So at this point, once we remove brand, we have significant effect for all remaining variables. So this here is going to be our simplified model, or our simplest model. There. So we've got our simplest model. ANOVA mod.sim. Right there. So we've got our simplest model. What's next? All right. So what are we doing? Yep. So we've got this interaction. So in order to investigate this interaction, we're going to have to account. We're going to have to control for one to look at the effect of the other. What about light? What can we? I'm sorry, not light. Variety. What can we do with variety? Okay. How many varieties do we have? Yeah, just two. So for variety, let's do this. So we'll start with variety. Okay. This is a two-level variable, right? So at this point, we already know the effect. Right? We already know it's significant. So weight is a function of variety. So we can just look at this now and say, yep, mild gives larger weights than early. We're basically done with that. That's our interpretation. But Now we need to make controls. We need a control for water, look at the effect of light, then we need a control for light and look at the effect of water. All right, so how did you do that? Subsets. So how about light? Let's say the effect of light, all right? Control for water by creating subsets. We're doing light, right? Are we doing light or water? Just forgot. Effective light. Create subsets for water. All right, so create my subsets, low, medium, and high. Now what we need to do is look at the effect of light in our model. How did you do it? Mod dot low. Use LM, right? Use weight. What else? Okay, data equals low.
Water.
Okay, light. What else? Is that it? Does everyone agree? What's that?
Oh, sorry, I was just realizing I read this wrong.
Yeah, so we created this low water, right? Looking at light. Did we do it right? What are we missing?
Is it supposed to be effective?
Variety is significant. So since variety is significant, it's going to have to carry into any of our future models. Unless it was part of a three-way interaction, we're doing subsets of subsets of subsets or whatever, right? So we don't care about variety. We're not going to interpret variety. We already did. All right? We already made our plot variety. We know one variety is going to be higher than the other. But we need to account for it before we look at the effect of light. So we have to include it in our model. So at this point, I mean, is it going to change anything? I don't think so. I think all of our p-values are like super small. But we have to include it. Any of the main effects that are not a part of our interaction term, they need to be included. So I'm just going to go through here, update all of these because we're making our subsets. Run them all at once, and you will see that we have significant effects for all of them. So how do we run our two keys?
For each one. A or B.
Yep, we're going to run each one. We're going to run two key HSD on the AOV of each model, because that is going to allow us to take into account that other variable before we look at the effect of light. And I don't know which one we're going to see. Yep, sun versus shade. Hold on, light is only 2 levels?
Okay.
Yeah. So we didn't need it. Thanks.
No problem.
But that's just 2 levels, so we know that. Just make a plot, look at it, or calculate averages, and you're good. Now, we need the effect of water, right? control for our light. Got all of those. Sun and shade. Shade, there's our subsets. And we've got our shade. Again, left variety in there. Look at our ANOVA table. It's significant. Run our 2 keys post hoc test. Everything's different, right? All water had an effect. Had sun. Significant. Everything's different. So when you go back and look at then the plots for kind of figures and write-ups, which ones do we use? Scroll up. See what this looks like. Use an interaction plot for the terms that have significant interaction. This right here demonstrates, yeah, we've got a difference. The slopes are not equal. So that shows we have a significant interaction. It shows the pattern, right? It shows the pattern that medium had the highest weights, high amount of water had the lowest weights. So kind of in the middle, medium type of water generated the largest jalapenos. And then we need one more graph to account for variety. Graph probably. You can do something like this, or in the results you can just give the means and standard errors. Questions? How realistic is this to do it all longhand? Maybe you do it. But once you start getting to these 4 variables or more, we typically start using other methods of simplification. Right? Start to use other methods of simplification. That's where we're going to be moving to. So we're going to learn information criterion. We do have randomization, but we're not going to cover it. If we need p-values for randomization, come talk to me. I'll help you out. And then it kind of gets into a philosophical issue of how do you actually randomize to generate, how do you randomize to actually assess a single variable or significance of a single variable? All right, questions on jalapeno? Yep.
So if we would have had like if brand was significant, but the interaction effect between water and light was still the only significant one, we would just have to do a whole nother ANOVA plot for brand separately as well.
Or what?
I guess that'd be 3 ways. I was saying, so it, instead of just variety being significant, if brand was significant, would you do the same thing as variety? Just
yeah, you would include them. You would use your 2 keys post hoc to look at brains at that point. So if you had another main effect that wasn't part of the interaction term, yeah, you still have to continue with post hoc. What happens? What happens if we do a 2 keys on this simplified model? What do you think is going to happen? Lowercase u. Yeah, yeah, it gets it all. So if you had if you had 2 or 3 main effects, go ahead and look at that. You can use 2 keys on that. It'll split it out, and it'll take into account that the population pulled standard errors. controls for your type 1 a little bit better than just kind of making your simplified model. This is kind of one of these effects. If you didn't have this significant interaction term and you ran this, all of those p-values, well, not all of them, you could have some significant p-values. You'll have some that are not significant, but we can't rely on that because we could have had, you know, could have increased your type 1 error rate slightly. But in this case, yeah, all of these, this is the interaction. This is all different possible combinations of water and light. And with the significant interaction, you should see differences between these individual groups. Some people would use this and say, well, I have a difference between medium shade and low shade and so forth, but it just becomes very, very wordy, very complicated. Show a figure, talk about the interaction, state the general trend. Any other questions? All right. So that's all with our situations where our assumptions are met. And I think what you're going to see that when we violate our assumptions, it might actually be a little bit easier. All right. So this is posted it this afternoon. Remember to post it. This is going to apply whenever we have three-way or more. Two-way ANOVAs or regular one-way ANOVAs, it's probably easiest just to go ahead and do like Welch's ANOVA or permutation test. All right. But once we have two-way or more, once we start having interaction terms, it becomes a little bit harder to do some of these randomization tests. All right. So classical tests only applicable when our assumptions of ANOVA are met. All right, I've got a quick review up there of the assumptions. If we violate the assumptions, and there are some exceptions to this, then we really have only two options. One, we can do a randomization test, like we learned with regular ANOVA. All right. You can do randomization tests. Nice thing is that we get a p-value. Right? We're using our own data to generate that null distribution. The problem is that you can only compare nested models. Right? So you can't compare models that differ in their terms. They have to be nested. And number two, once you get more than two variables, it becomes nearly impossible to come up with a randomization method that maintains our the correct null hypothesis. For that reason, our second option actually becomes much better and much more favorable. And that is simplifying our models based on information criteria. All right, the one that we're going to use is AIC, Keki's information criteria. All right, this allows us to compare both nested and nested models, which is important because you'll see if we have 4 or 5 variables, that's a lot of models that we're going to compare, and we could get to a spot where we're not comparing nested models anymore, but one of those models is actually better, simpler, and that's the one that we choose. Now, no matter which one we choose, they should both generate the same simplest model in theory. Just like if the assumptions are met and we did classical tests, the simplest model from the classical tests should match the simplest models if we do it this way. And that's why I said, once we start getting up, even if our assumptions are met, it's probably easiest to do this AIC to quickly find the simplest model. Nice thing is, more and more people are accepting it. All right, they're accepting it as being a valid way to find a simplified model. So what we're going to do is introduce this using collegegrad.csv. Our data file that's posted. What this did was reported on starting salaries for recent college graduates. All right, the graduates were classified based on state, based on the type of school, public or private, based on their major, and the major was just either a science major or a non-science major. And since we're in science department, you could imagine my preference on who's going to make more money. as well as time of graduation. So did you finish in less than 4 years? Did you finish in 4 to 5 years? Or did you finish in 6+ years? All right, so the question is, are any of the explanatory variables significant predictors of starting salary following graduation? So here you have high school student who doesn't know what their major is going to be. They're only concerned about making money, and they say, okay, what do I need to do to make the most money when I graduate? So go ahead, download it, get it into R, check the assumptions, figure out which assumptions were violated. Get the assumptions checked. You can often see it in function 1, function 2. Get the assumptions checked? Yep. All right, so got it in. Made full model. I'm gonna check both. So GVLMA, I used global stat. Definitely violated it. P-values like off the charts low. All right. If we check you know, if we're curious which one did we violate, well, it looks like it's skewness, it looks like it's kurtosis, so it looks like we're non-normal, is what it kind of looks like. Heteroscedasticity, maybe. That could be due to the skew or kurtosis. I think this part, not really. I'm probably not worried about it increasing in size. You know, like trumpet shaped, it does kind of look like it's random, but this is clearly non-normal, the QQ plot. So this tells me, you know, we've got problems. Even here, scale location, you can see, not really, pretty much horizontal line, and our outliers are looking pretty good. All right. So that's kind of what we were going with. All right, so now we can't really do, I mean, we could do our classical test. I could say, run the classical test, come up with your simplest model, just to demonstrate that we come up, that we might be able to come up with it. Because remember, ANOVA is pretty robust to violations of normality. Even more so if we have equal sample sizes. I don't know if we have equal sample sizes. But we're not going to do that. What we're going to do is go through model simplification using information criteria. And a big term for this is that we're actually looking at deviance. All right, deviance is just a fancy term that describes variation around our predictor value. All right, we talked about like a deviate. All right, the squared deviate, that's the difference between our predicted values and the observed values. All right, our least squares method tries to minimize the square differences. All right, with the information criteria, what it's going to do is calculate a log likelihood value, which represents deviance of our entire model, and then it's going to penalize it based on the number of parameters of the model. So as we start adding more and more predictor variables, we should account for more and more variation. But we get to the point where, yeah, we're adding more variables, but we're only just we're making it more complex. It's not really improving that explanation. So that's where our penalty comes in. All right. So yeah, you can do a great job by including every single possible variable in there, but it becomes extremely difficult. So our log likelihood value is going to look at the variation between our predicted model and the actual data. All right. And then what it's going to do is calculate this information criterion that penalizes the number of variables that we have in our model. So the more variables, the bigger a penalty. And what we're going to do is compare our AIC values for our information criterion values for different models. And our preference is always going to be one that has a smaller information criterion. So the best fit model, in theory, should have the lowest log likelihood, the least amount of deviance around that predicted model. Right, now there's a catch because our log likelihood decreases and could become negative as we start to explain more and more variation. But so you could be looking at negative values, and if you are looking at negative values, just remember, we're looking at the more negative values as being better. So what we're going to do is keep simplifying models until we get to the point where when we remove a term, our information criterion goes up. And if it goes up, that means we've just took out a term that explained a lot of our variation, which now means we have a lot more deviance in that model. So we better put it back. So what type of information criterion do we use? A Keki's information criterion is one that you've probably seen before. It's an AIC. The other type is a BIC, which is Schwartz-Bayesian criterion. All right. We're not going to use it. Some people do, but we're not going to use it. It's a little bit more complicated to calculate, but AIC works. AIC is acceptable. Some of you may be using it now. I believe. Who's using it? Cameron. For one person. Yeah. She learned about this 2 years ago. All right. See, when she read the paper, she said, "Yeah, I know what that is." I hope that's what she said. Yeah, a Keki's information criterion. All right. So we're going to use this. We only use this type if we're fitting with maximum likelihood, which is what our basic ones are using. If we start doing like logistic regression or mixed effects models, we'll have to switch. All right. There's also this AICC, which is a second order AIC variable. We use that when our sample size divided by the number of variables is less than 4. All right. And I'm going to say this is the default if we use the dredge function in the mu-min package. All right, so I believe Cameron's also using this as well, that package. And I'm going to show you how to use it too. And I know we're using the dredge package, but you'll know. We'll talk about it when we get there. BICs, we're not worrying about. All right, so how are we going to simplify the model? We're going to start with our, we're doing 2 different paths. All right, so we're going to start with our full model. That most complex model, we're going to calculate an AIC, and then we're going to start removing terms, one at a time. All right, and we're going to keep choosing models that have the simplest term. Now, if we did this by hand, I'm gonna do it this way. A, B, A, C, B, C, plus A, B, C. Zoom in on this. All right. So if we were doing it by hand, what we will have to do is we start with our full model. And just simple, A, B, and C, that's our group. Those are our 3 variables. We start with a full model that has 3-way interaction, all the 2-way interactions. What we would do is start with this term. So we calculate an AIC for that model. And then we compare it to an AIC where it is with just our 2-way interactions. All right. If this AIC is lower than this, then this is the better model. So then we go to the next step. This is our new model, our starting place. Now what we're going to do is compare it to three different models. This over here. C plus BC. Now we compare it to 3 different models. Because again, you could say, well, how do I know which one to remove? You don't. So what you're going to have to do is remove them, each one at a time, and compare it to the AIC. Compare the AICs of each of these. And again, keep choosing the model that has the lower AIC. So you can see, with 5 variables, it basically becomes unmanageable. However, there is a simplified method. All right, and there's a function in R that'll do that. Now, can we ever add a variable back into our model once we remove it? Oh yeah. That's what this is going to do. It's going to remove a model, it's going to remove a variable, it's going to add a variable back to it, and then make the comparison with the AICs. In doing this, we're not restricted to only comparing nested models. We can compare non-nested models, and each time we're going to prefer those models that have the lowest AIC. Now, what happens if our AICs are really close to each other? I don't want to say by rule, but say by consensus, or perhaps half consensus, or wherever you want to go with that. We set the limit at 2. So if our AICs are less than 2, then there's no difference between the models. In other words, we can't resolve which one is the better model. If it's more than 2, yeah, you take the one that's smaller, without a doubt. But if you get into the situation where the 2 models only have a difference of 1, we don't know which one's best. We don't know which one's best. And in that situation, generally, you're going to choose a simpler model, the one that's less complex, unless both have the same number of parameters. So going back to this situation, where you have this AB plus AC term, or you have AB plus BC term, perhaps you look at these and they have a difference of 1, and these two are definitely lower than this one. Which one do you choose? Well, that's up in the air. That's kind of a problem. At that point, you could say, well, AB is probably needs to be included, and then we don't really know how significant those would be. Those remaining 2 terms would be. It's a problem. It's a problem, and it's a problem in interpretation of our data. If we need to pick one, there is something called model averaging, which will start to kind of generate some random data to see which ones, or random data. Remove some data and regenerate your values, regenerate the AICs, just to see how much emphasis or how much weight each of these parameters have in our model. That's going to be beyond the scope of this course. So how do we go about doing this? There's a function called step. All right, and the step will automate the process for us. We basically give it our full model, and we tell R, we're going to step through the model to find the simplest model. All right, and we can set a range. So we're actually going to set like the simplest model that we can have and the most complex model, because the step is going to go backwards and forwards. It's able to remove terms and add terms back into the model until we find our lowest AIC values. Big benefit of step is that you can actually see the process of adding and dropping terms. R will output what it's doing in each step. Disadvantage is that we have to be diligent in making all possible models. All right, there could be a situation where the function itself drops some terms, and as a result, we don't necessarily get all of the models to compare. All right, so then we kind of have to force it to get to some of those models. Also, since it's automated, it's going to keep dropping terms until it gets to the lowest AIC. But if you have a lot of terms, it's possible that you hit what's called a localized minimum. So you get to a spot where you're at a low AIC, but it's not the actual global low. That's down here. But in order to get there, we've got these other terms that'll cause an increase in our AICs. We'll see some of those, and we'll talk through some of these. The alternative is to use the dredge function. That's in the mu-min package. I'll show you how to do that. The nice thing about that is that the dredge function will produce all the models, generate all the AICs, and then say, these are your top models. These are the top ones with the lowest AIC. All right. Now, while that's great, we don't have to worry about getting all possible models. You might fail to really consider the problem at hand. You know, what our overall goal is. All right, it's one thing to say, well, I want the simplest model, I want the best predictor model. It's another to understand why we want to do that and how we actually get there, which might not really be a problem. So here's our step function. All right, we give it the model, our starting model, and then we list the scope. And the scope is going to be the lower model, the simplest model, and the upper is going to be the most complex model. And what we're going to do is create actually 2 models. We're going to create the full model, and we're going to create the null model, which has no terms. It's just our dependent variable squiggly 1. So we've got the most complex and the simplest possible model that we can have. And we're going to run this both directions. So we're going to allow it to start full and work towards simpler models. We're going to start with our simpler models and work to a more complex model. Hopefully, both of those will produce the exact same simplest model. And if it does, then we found our simplest model. All right, so I've got rules on how to do this, or examples on how to write it. I say let's just jump right to our model at hand. All right. So we have a full model. Did you run it? Did it work? All right, so I'm going to create a null model. Because this is going to be the lowest model that we can possibly get. And that, yeah, I'm gonna, we're doing college. So we're gonna create our null model at this point. And for the null model, we're trying to predict salary. So what's to the right of this squiggle? What's that? 1. 1. So in our ANOVA, when we talk about regression summary, we talk about in the summary of the model, it gives the F and the P value, and we said this is always in comparison to a null model. Did our model do better than the null model? This is our null model. It has no terms. It's just going to use the average salary as our predictor. All right? So we create our null model. And then what we're going to do is use the step function. All right, we're going to step. We're going to start with the model full. But we have to give it a scope. All right, so we're going to start with our full model. But we're going to give it what our simplest model is, or the lowest model that we can have, as well as the highest model that we can have. So this is actually going to be pretty easy. It's going to be mod null and mod full. And then the default is to do it both, backwards and forwards, which we're just going to leave it. All right, so we're going to start with the full model, and we're going to try to find the simplest model by going backwards first, and with the occasional adding in of the new variable. So when I run it, it generates a lot of output. All right, so go ahead and get yours run and see if this works. All right, what's the error?
Like a paragraph.
It's what?
Like a paragraph long here.
All right. So this is going to give you a bunch of output that we don't necessarily need. But I'm going to show you what's going on. So it starts. AIC of our full model is 4218.13. Now we always want to go low. We want to get to a lower AIC. So the first thing that it's going to do, oh, it says for the start, that's our starting model. So all interactions. If it does nothing, that's our AIC. If we remove the four-way interaction, our AIC increases. Right? Is that what you guys got? Yeah. So what does it do at that point? What does R do at that point? Keeps it. It stops. Because it's a computer. What I'm going to say, it's a dumb computer. In the programming it says, if the AIC decreases, that becomes our next new model, and we continue with our simplification. Did this AIC decrease? No. So its simplest model, according to R, is this four-way interaction model. And it gives all of the coefficients. These are the coefficients that you would get if you looked at the summary. So this is, let's see here, grad 6, negative 15.92. There it is. So those are the same coefficients that gets reported from the summary. That's not what we're at, right? For us, we can look at this AIC. What's the difference in our AIC value? How different is it? Less than 2. Less than 2, 1.1. All right. Is that a significant difference? No. So for us, we can't resolve these two models. We don't know which one's best. All right. And by rule, then, we would typically go to the simpler model to do that. All right. Now, I don't think we're at our simplest model yet. So what I'm going to do is start from the beginning. So now I'm going to start with our null model. We started at the full one and try to work backwards, and I'm going to consider that a massive fail. Left everything completely in. Now I'm going to start at the bottom and see, do I come up with the same simplest model? Is it going to work forward to where we have all 4 terms? So I'm going to run step. We're going to do this mod.null. That's where we start. And our scope is going to be the same. We're going to start at the null model. Our upper is going to be the full model. So that's going to be the maximum that we can get. And I'm going to run it.
Where did it all go?
Thinking that's not right.
Where did it all go? Mine did the same thing.
Yeah, I have the same.
Where did it all go?
No way. It didn't calculate it. Didn't calculate it.
Over?
I don't know if this made a difference or not. I guess it must have. All right, so note I have lower and upper. I've got alternate ways to kind of write it. I think that had an effect actually, because when I when I did lower equals mod.null and upper equals mod.full, now it runs. So must have to include it.
So it's just lower equals.
Yep. Yeah, we're setting our lower bound and our upper bound. So again, with the output, we started with our null model, salary as a function of 1. We have our AIC, 4711.1. And the first step is to add each of our main effect terms and calculate an AIC. That means that we're not adding them all one at a time. We added 1, calculated the AIC, because what we want to do is compare or figure out which one gets added first. So when we added school, AIC went to 4353.2. When we added time.grad, it went to 4633. When we added major, it was 4692. When we added state, it was 4714. State was the only one that caused an increase. All right? So what it's going to do is R is going to look at these and say, okay, what one is my lowest AIC value? That's the one we're going to add next. So now that goes to our next step. We have salary as a function of school. We have a starting of 4353.21, a starting AIC of that. And now we're going to add each of the remaining main effects terms, as well as subtract one of the terms, and calculate our new AIC. So when we have salary as a function of school and we add time.grad, our AIC dropped to 4232. Right? It dropped. Now when we added state, it increased again. So you can see that, okay, time.grad caused the largest increase in the AIC, so now that becomes our new starting place. That's our new starting model that has the AIC value. We're going to check, we're going to add major, we're going to add the other two, we're going to add our interaction. So now that we have school plus time.grad, now that we have two variables, we can add an interaction term. So R adds the interaction as individual values, calculates AIC, and it says, okay, when we add major, it results in our largest AIC, largest decrease in the AIC. So that now becomes our next model. And it repeats. Now it goes, we have school, time.grad, and we have major. So now we can add all of these two-way interactions along with the remaining main effects or possible main effects. And what we see is that when we add the major and time.grad, we do get a drop in the AIC. We get a drop of about 8. So R adds that interaction term and goes back and adds, and it also drops terms from our model just to compare AICs. And what you see is at this point, no matter what we do, we always increase our AICs. We always increase the AICs. Now, if we add this interaction term, the school major, the AIC results in a less than 2 increase, right? Less than 2 increase. If we add state, it's just above 2. So the school major interaction, maybe it's going to add significant amount of variation, but at least for AICs, we can't really resolve which one's better. And because of that, we typically choose the simpler model, which is this one that we just finished with. All right? So I can copy that. Copy that line, which is really nice because it's already written up as LM. Copy it, paste it into a chunk, call it mod.simp, and now we have our simplest model. Is that the same simplest model that we got when we worked backwards? Nope, we didn't. All right, so we're not quite done. We're not quite done. We need to see if we can get back to this model. All right, so what we'll do is we'll stop here, and on Monday we'll pick it up. And if you're curious, oops, open up. Full. If we did it with our jalapeno data, it can't resolve this light-brained interaction term. So if it can't resolve it, we go ahead and remove it. We take the simpler model and we would proceed with our simplification. So now that that light brain is out, then we have to see, well, what happens if we drop brain with the model? We're not quite done. So yeah, even if our assumptions are met, this AIC should produce the same simplest model as long as we remember our rule about the difference of 2. All right? right. Let's call it a day. Pick this up on Monday.
How's your enthusiasm, like, Toby? Getting right back to it?
So I'm trying to